Okay. So I am recording right now. Everybody say hi. Okay. You probably didn't hear them, but everybody says hello. So we're looking at the Riemann sums, and that p that's called the Norman p, that's the widest interval. And so as that gets smaller and smaller, our Riemann sum approaches the actual area. Okay, look at the bottom, right? So, yes, we got a question. No, no, no. The question was, do we have to remember everything in the blue? And the answer is no. So what we're doing is like what we did in the first part, where we would look at how limits are the basis for finding a derivative. You remember that? Like the changes, as the changes get smaller and smaller, take the limit as it approaches zero, and that's the instantaneous rate of change instead of like a estimate. So what's going on is this big messy stuff right here. This is saying that the exact area, so it says equal, right? It's not approximately, is a limit. So this means the norm of p. The widest interval, the widest subinterval, is this number. Okay, it's called the norm of p. As that gets closer to zero, the width of those rectangles gets closer and closer to like just a little line segment almost. And they can fit more and more perfectly underneath the curve. Now this is just a multiplication. Okay, the delta x is right here, the change. Now it says sub k because for intervals, they could have different widths. You could have this as 1, this has a width of 5, this has a width of 2. So it's a little messier right here, okay? Because it's saying each time you have to look at the specific width, and then the function value would be the specific height at that value. So it's just length times width over here. And this is the partition from A to B, so from one point to the other. Now we're going to simplify this a lot if we look at what if the intervals are all the same size, okay? So before we do that, let's see if I can move this. This big complicated thing is what we would call the definite integral. It's called definite because it's for a specific range of values. Okay, if we just looked at the indefinite integral, it would be a function, but there'd be no specific value because the function might have a domain from negative infinity to positive infinity. So if you imagine the area under a curve that's infinite, like a parabola, its indefinite integral, there would just be an infinite area. The definite integral is looking at what's the area under a curve from one x value to another. Okay. All right, so that's where that interval a to b, just between a and b. Okay. So let's see if we can get this to progress. This is where we're going to simplify it a little bit. So this part up here, delta xk, that in this says it can be all different lengths. We're going to say if they're equal length, just subtract b and a, that's the width, the total width, and divide by the number of rectangles you're using. So if you're using 4 rectangles, you take the total distance divided by 4, and that's the width of each one. If you're using 10, you divide by 10, and the rectangles get skinnier and skinnier and skinnier. Okay, so this shortens down to this. So on the bottom, now what we're doing, all the rectangles are the same width. So this delta x times f of c sub k is like c1, c2, c3, and you're counting from 1 to n. So when you do the first, let's say that you have an n of 1, it's just one rectangle, right? You estimate it with one rectangle. It's not very good. Then you estimate it 2 rectangles. Okay, you have a sum of 2 things. And what we're saying is we're taking a limit as you're getting those rectangles closer and closer to infinity. Okay, then we get to here, Leibniz. So he introduced, instead of writing all of this, he condensed all of that to this symbol on the right. Sometimes it looks kind of like a long stretched out S. You see that? So this is the symbol for integral. A and B tell us the starting and ending x values, or the end values for the interval. Okay, f of x is referring to the function we're trying to find the area under. And then these dx's are the very small changes. This delta x becomes dx. So it's kind of like his notation was you're going to multiply this times this, and it gives you areas. And as these approach smaller and smaller values, that approaches the actual area. I'm going to pause right here.